Reasoning by resolution. Reasoning by resolution is another deduction method for propositional logic. It is, for example, used in automated theorem proving for an application. The main idea of it is that it is based on a single inference rule called resolution rule. Resolution is based on proof by contradiction. This means that to show that the propositional formula B can be derived from a collection of propositional formulas A1 to AN, we show that the collection A1 to AN, including the negation of B, is contradictory. First of all, to start the resolution, propositional formulas are required to be in conjunctive normal form. This means that the propositional formula can be written as a conjunction of formulas C, where each C is a disjunction of literals. A literal is either a propositional symbol or a negated propositional symbol. So, A can be written as a conjunction C1 to Cn, in which each Ci is a disjunction of Q1 to Qmi, where the index mi depends on the other index I. Next step in the resolution method is to encode disjunctions of literals as sets. So we have this formula C, which is a disjunction of literals Q1 to Qm. And we make a set of it as the set of Q1 to Qm. And these sets are called clauses. For example, the set of P0 or the set of negation of P0 and P1, and even the empty set are clauses. We can then extend the concept of evaluation to clauses by setting that the value of the clause C under valuation V is 1 if and only if VQ is 1 for some Q in C. So the idea is that this captures the truth of a disjunction. It is enough for a disjunction C to be true as long as one of its disjuncts is true. Finally, we turn these formulas in conjunctive normal form to sets of clauses, written as script C is the set of C1 to Cn. Each of these Ci's are sets of literals. We extend the concept of evaluation by setting V of a set of clauses script C to be 1 if and only if V of C equals 1 for all clauses in the set of clauses script C. This captures the truth of a formula in conjunctive normal form. All of the conjunctions need to be true in order for the formula itself to be true. A very special case in resolution is the empty set, for which V of the empty set is 0 always. And we call in this setting the empty set as a contradiction. Let us now look at an example. We have a formula in conjunctive normal form, which is a formula of 3 conjuncts. First of which is a disjunction, so it is not P0 or P1 or P3. The second is P0 or not P1 or P2. And the last one is not P3. We turn each of these conjuncts into clauses which are sets of literals. So the first one produces the set not P0, P1, P3. The second one produces the clause P0, not P1, P2, and the last one, the singleton, not P3. You may now pause for a moment to think if there is a valuation v for which v of this set of clauses is 1. So is there a valuation which makes the set of clauses true? The proof by resolution method has only one inference rule, which is called the resolution rule. The rule is applied to clauses which are sets of literals. Here we see the notation. On the above of the bar we have the assumptions. First assumption is a set which is obtained by combining a certain clause which we denote by C1 and we add to it the literal pi. The second assumption is another clause C2 and we add to it a literal not pi. So we have the same propositional symbol in above the line, first as itself and then negated. And from these assumptions we can infer a set C1 combined with C2, which is a clause, and you may note that the literal pi and not pi are dropped because they make a contradiction. So the idea here is that if two sets of literals combined would make a contradiction, then the contradictory pair of literals is taken out. Now, a resolution proof of a clause C to be understood as the conclusion from a set of clauses script C to be understood as assumptions is a sequence of clauses C1 to Cn where first of all each Ci is either from the set of assumptions script C or derived by using the resolution rule from earlier clauses. And second, the last clause Cn in the sequence is the conclusion C. We write script C turnstile R C if there is a resolution proof of C from the assumptions script C. The method of proof by resolution is sound, meaning that it preserves truth. This is so because the resolution rule itself is sound. To see this, let us look at the rule. As assumptions we have, first of all, the clause C1 combined with the literal pi, and as the second assumption we have clause C2 combined with not pi. And from these assumptions we conclude the clause which is the union of clauses C1 and C2, and the literal pi is dropped. So assume that these assumptions are true. So for all valuations we have that v of C1 union pi is 1 and v of C2 union not pi is 1. We have two cases. So if pi is true, then its negation is false. But in order to the second assumption to be true, we must have that the valuation gives the value 1 for the clause C2. And this gives that the valuation gives value 1 for their union. The second case is that the valuation gives value 0 to pi. So it must be the case that the valuation gives value 1 for its negation. But similarly, then the valuation must give value 1 for the clause C1, and again the union of the sets C1 and C2 gets the value 1 under the valuation V. Even though the method of proof by resolution is sound, it is not complete. This means that one cannot prove by resolution all consequences of a set of clauses. Let us consider for a very simple example. We have only one assumption, which is the literal p0. and we cannot derive the clause P0 and P1 from the assumption P0, even though the formula P0 or P1 is a logical consequence of the formula P0. This is so because we only have this one assumption P0, and in order to apply the resolution proof rule, we need to have two assumptions which are different sets, and this is not in this case possible. While resolution is not complete, it is what we call refutation complete. This means that from a contradictory set of clauses, the empty clause, which is the empty set, can be derived. So while not all consequences of a set of clauses can be derived, we can check whether a propositional formula is a logical consequence of a set of clauses. For example, in this case we have the assumptions P0, not P0, and not P1. And from these assumptions we can infer by resolution the empty set, which shows that the formula P0 and negation of the disjunction of P0 and P1 is a contradiction. But this means that P0 or P1, the formula, is a logical consequence of P0. Details are left as an exercise. So we may use the refutation completeness to show proof formulas in the following way. To show that the propositional formula A is a logical consequence of assumptions B1 to Pn, we first transform the assumptions to conjunctive normal forms and turn those to clauses. Second, we transform also the conclusion A, or rather its negation, to a conjunctive normal form and add that to the set of clauses. So now we have assumptions, several clauses, and then we apply the resolution rule to these clauses until the empty set, i.e. a contradiction, is derived. It may also happen that it is not possible to derive new clauses by the resolution rule, so not even the empty set, and in this case A was not a logical consequence of the assumptions after all. Finally, we show how to find conjunctive normal forms. First, for simple formulas, we use rewritings, like we write the implication P0 implies P1 as the disjunction, not P0 or P1, and so on with other known rules like De Morgan's and distributive rules. There is a systematic method by using truth tables. If we have a more complicated formula, we produce a truth table for it, and to the conjunctive normal form we pick those rows which give the value 0 for the formula. For each of these rows we form a disjunction, putting in Pi to the disjunction if Pi is 0 or false, and the negation of Pi if Pi is true under the valuation V. And then we form a conjunction of these disjunctions. As an example on how to write a formula in conjunctive normal form, we take the formula P0 or P1 implies P0 and P1. And when we form the truth table for it, in the first row P0 and P1 are true, the formula is true. P0, in the second line P0 is 1 and P1 is false. This gives the value 0 to the formula. Third line P0 is false, P1 is true. Again, the formula itself is false in this case, and the final case P0 and P1 are both false, and this makes the formula P0 or P1 implies P0 and P1 true. For the conjunctive normal form, we pick those lines which give the formula the value 0. So they are the second and third. And we produce the disjunctions. So from the second line we read the disjunction not P0 or P1. From the third line we read the disjunction P0 or not P1, and we combine them to a conjunction. And this is our conjunctive normal form for the original formula. When written as a set of clauses, this gives us the set of two sets, first of which consists of the literals not P0 and P1, and the second is the set P0 and not P1. Note that from the same table we can read the disjunctive normal form from the first and the last line, which gives the formula P0 and P1, disjunction with not P0 and not P1.